Welcome back to our series on geostatistics in mineral exploration. In our last video, we covered the basics of data types. Today, we're diving deeper, starting with a fundamental concept, the difference between a population and a sample. In statistics, the population is the entire group we want to understand. The sample is a small, representative part of that group that we actually analyze. This is crucial in mining. Imagine a gold mine. The population is all the rock in that mine, potentially millions of tons. It's impossible to analyze every single piece. So instead, geologists take a sample, like pieces of a drill core, and test them for gold. The goal is to use the results from this small sample to make accurate predictions about the entire mine. But how we collect that sample is just as important as what we find. The method determines whether our sample is truly representative or biased. Let's look at the main sampling techniques used in exploration. First is simple random sampling. Here, every part of the population has an equal chance of being picked. Think of it like randomly plotting points on a map of your claim and taking a soil sample at each point. It's simple and unbiased. However, if your mineral deposit is patchy, you might miss the good stuff just by chance. Next up is stratified sampling. With this method, you first divide your area into subgroups or strata based on known features like different rock types. Then you take random samples from each subgroup. This ensures you get a good representation of all the different parts of your study area. The only catch is you need some prior knowledge about the geology to define your strata correctly. Then we have systematic sampling. This is very common in geology. It involves taking samples at regular, fixed intervals, like collecting a rock sample every 10 meters along a drill hole. It's easy to organize and gives you even coverage. The main risk is if there's a natural, repeating pattern in the mineralization that happens to line up with your sampling interval, which could skew your results. Another method is cluster sampling. Here, you divide the population into clusters, like a grid over a map, and then randomly select entire clusters to sample completely. This can be very efficient and cost-effective, especially for large areas, but you might need more total samples to get the same level of statistical confidence as other methods. Then there's purposive sampling. This is where a geologist uses their expertise to deliberately pick samples they think will be most informative. For example, they might target rocks showing visual signs of alteration that are often linked to gold. This is great for early-stage exploration to quickly test ideas, but it's highly subjective and not suitable for formal resource calculations. Finally, we have convenience sampling. This is exactly what it sounds like, taking samples that are easy to get, like along existing roads. It's fast and cheap, but it's also extremely prone to bias and not scientifically recommended for any serious analysis. Okay, so now we've collected our data using a structured sampling plan. What's next? We need to analyze it. This brings us to exploratory data analysis, or EDA. EDA is the critical first step in making sense of your data. It involves using stats and visuals to understand its structure, find patterns, spot anomalies, and check data quality before you do any complex modeling. Its importance cannot be overstated. A good place to start is by assessing the central tendency, which means finding the center or typical value of your dataset. The three main measures are the mean, median, and mode. The mean is the average. The median is the middle value when the data is sorted, and the mode is the most frequent value. In geochemistry, the choice matters. The mean is very sensitive to extreme values. One single high-grade sample can pull the average way up, giving a misleading picture. The median, being the middle value, isn't affected by these outliers. This makes it a much more robust and realistic indicator for skewed datasets, which are common in mining. Next, we need to quantify the data's dispersion, or how spread out it is. Key measures include the range, variance, standard deviation, and the interquartile range. To see why this is important, imagine two sets of gold samples. Both have the same mean of 50 grams per ton, but one set has values all over the place, while the other has values tightly clustered around 50. They have the same center, but their variability is completely different. The mean alone doesn't tell the whole story. We also need to characterize the data's distribution or its shape. You've probably heard of the normal distribution or the bell curve. We use two key measures to describe how our data deviates from this ideal shape: skewness and kurtosis. Skewness measures asymmetry. A positive skew, with a long tail of high values, is very common in mineral deposits. Kurtosis measures the peakiness of the distribution. Here's where a powerful concept comes in, the central limit theorem. It states that even if your raw data isn't normally distributed, the distribution of the average of many large samples will be. This is a cornerstone of geostatistics, allowing us to use powerful statistical tools that assume normality. Of course, numbers alone can be hard to interpret. That's why data visualization is essential. A histogram shows the frequency distribution of your data, letting you quickly see its shape, center, and spread. A box plot is fantastic for identifying the median, assessing dispersion, and spotting outliers. And a scatter plot helps you see the relationship between two different variables, like whether gold concentration is related to arsenic levels. But before we can trust any of this analysis, we have to make sure our data is clean. Raw data from the field or lab is rarely perfect. It can have missing values, typos, duplicates, and other errors. A systematic data cleaning and pre-processing workflow is absolutely essential. This workflow includes several steps. First, handling missing data. You might remove records with missing values or use statistical methods to fill the gaps. Second, managing outliers. These extreme values can be deleted, replaced, or kept if they're considered geologically real. Third, correcting errors. This means standardizing text entries and fixing typos. Fourth, removing duplicate records. You also need to standardize units, convert data types to the correct format. And finally, resolve any logical inconsistencies, like a drill hole sample where the end depth is shallower than the start depth. With a clean and validated dataset, we can now explore the relationships between different variables using multivariate analysis. These relationships often reflect real geological processes. Correlation analysis is a key tool here. It measures the strength and direction of a linear relationship between two variables. This is how we identify pathfinder elements, which are elements associated with our target mineral. For example, a strong positive correlation between arsenic, antimony, and gold suggests that arsenic and antimony can be used as indicators to guide exploration for gold. For more complex data sets, we can use factor analysis. This technique simplifies the data by identifying underlying factors that explain the patterns of correlation. For instance, it might group a dozen different elements into just a few factors that represent distinct geological processes like magmatic differentiation or weathering. Now that we've explored the statistical relationships, we're ready for the core of applied geostatistics, spatial continuity modeling. This is where we move from asking what the data values are to where they are. The main goal is to use our sampled points to predict values at unsampled locations. This process is called spatial interpolation. It allows us to turn a few drill hole results into a continuous map of grades, helping geologists visualize the deposit and identify high-priority targets. The fundamental tool for this is the variogram. The variogram measures how similar two samples are on average based on the distance between them. A typical variogram has three key parts: the nugget, which represents measurement error and very small scale variability; the sill, which is the total variance where samples are no longer spatially related; and the range, which is the maximum distance over which samples are still spatially correlated. To build a good variogram, we need to set a lag distance and a tolerance. The lag distance is the interval we use to group sample pairs, and the tolerance allows for some flexibility since geological data is never on a perfect grid. Finally, the variogram is used in a powerful interpolation technique called kriging. Kriging provides the best linear unbiased estimate for a value at an unsampled location. It uses the spatial structure defined by the variogram to assign optimal weights to the surrounding known samples. Closer samples and those in the direction of greatest continuity are given more weight, leading to a more accurate and statistically robust prediction. So let's wrap this up. We've walked through the entire geostatistical workflow, from sampling and data cleaning to exploratory analysis and advanced spatial modeling. The true power of geostatistics is its ability to transform sparse and certain data points into a continuous quantitative model of the subsurface. By rigorously accounting for spatial relationships, these methods provide a defensible framework for assessing risk, optimizing targets, and making confident economic decisions. Thanks for watching. If you found this informative, please like, share, and subscribe for more content on mineral exploration and geology. See you in the next video.